Hi, welcome to another edition of Calculus 2. We are going to continue our conversation about infinite series. We are talking about how to detect if a series converges or diverges. We talked about 10 methods for specifying this property. Today, let's go ahead and review all that we have learned so far so that when problems come up, which is a mix of these topics, we'll have some clues as to which one to employ. Let's go ahead and take a quick look at these. So, we had started talking about an infinite series. So, we have infinitely many numbers, we are adding them up. We want to know if the sum tends toward a limit or not. If it does, we say the series converges, otherwise we say it diverges. So we have to detect which one of these two it's going to be. One of the simplest tests that we can use to tell if the series diverges is that the nth term of the series does not go to zero. That is, if you take a limit of it, if the limit does not go to zero, if the limit doesn't exist, then we say that the series is not going to converge. Instead, we are going to say it diverges. However, we have to be careful that if the nth term does go to zero, that doesn't guarantee anything. So it is a rather weak test. The most important series perhaps in this section is the geometric series. That was a series that was made from starting with a number, and every time you multiply by a fixed multiplier and add up all the terms. General form of it, a r to the power of n, starting from 0 to infinity. We had a very simple criteria, and if the r, the multiplier, is less than 1 in absolute value, it converges. If it's more than or equal to 1, then it's going to diverge. And we have a simple formula in case it does converge, simply a, first term, divided by 1 minus the multiplier. That was the source of many other approaches that we took later on. Next, we had a few problems related to telescoping series. Telescoping series means that the first one can be written as a difference of two numbers, for example C1 minus C2, and the next one is the difference of C2 and C3, and the next one is the difference of C3 and C4, and so on. So telescoping simply refers to the cancellation of the of the consecutive terms, and such a series is going to converge if the nth term of these elements that are being subtracted from each other, if that one converges to a certain number, then the telescoping series does converge, and in that case the sum is very first one, c1 minus this limit. And if the cn does not have a limit, then the telescoping series is going to diverge. Next, we had an important series called P series, 1 over natural number raised to a fixed power P. If this power is larger than 1, the series is going to converge, otherwise it is going to diverge. Next, we had the case of the alternating series. Alternating series simply, as in if you have a1 minus a2 plus a3 and so on. Such series converge if the terms decline towards zero. If the terms decline towards zero, then the series is going to be convergent. And we had a simple way of approximating these things. If you want to know how close we are to the actual sum, we can go ahead and add up the first n elements. So we'll have the nth partial sum. The difference of the actual sum of the series from that partial sum is less than the next term of the series. So that one we use to figure out how many terms to add to reach a certain level of accuracy. Another test we had was integral test. Integral test, we have a series and there's a function. We know of a function that matches the terms of the series. That function is positive, continuous, and decreasing. If the integral of a function from 1 to infinity. If that one converges, the series converges. If the integral diverges, the series diverges. And we can also approximate how close we are if we add the first n terms. So the difference between the actual sum minus the partial sum of the first n series is less than the integral of our function on its tail from n to infinity. We had a root test. Root test said that if we take the nth root of the nth term, if the limit of that is less than 1, the series converges. If it is larger than 1, then the series diverges. And if it turns out to be exactly 1, well, we essentially have wasted time, and our test does not say anything. We say the test was inconclusive. The next one was the ratio test. In the ratio test, we took the ratio of the next to the previous one and took a limit of that. If that stayed below 1, the series converges. If it's more than 1, the series is going to diverge. We had a direct comparison test. It's for a positive series. If you have another series that converges and terms of that are more than the series we are looking at, then our series is going to converge. On the other hand, if we have another series whose terms are less than our elements of our series, and that one diverges, then our series is going to diverge as well. We had also limit comparison. In the limit comparison, we were looking at a secondary series. Both of these have positive terms. If the ratio of the corresponding elements has a limit that's larger than 0, then if one converges, so does the other one. If one diverges, so does the other one. So the property of one goes to the other. So we have 10 different tests or styles of looking at the series, and each of them gave us some handle on the issue. For all of them, it was important to notice that as far as the issue of convergence is concerned, we are only interested in the tail of the series. What the first few do, that's not going to influence the convergence or divergence. Okay, it's a quick look at 10 different styles of coming up with a verdict if something converges or not. And of course, the only way to know that we actually understood these things is to go ahead and take a look at a mixture of problems and see if we can tell which one of these things we should use. So we are going to end this short video here, and then we are going to come up with a whole bunch of problems related to these styles of series testing. Okay, so we stop here now, and then we'll come back and continue. Good luck and God bless.